Hello, I am Earl Nestor Velasquez, and today I'm going to present to you the amplitude shift key. Let's start. Digital transmission is the transfer of data over a point-to-point or point-to-multipoint communication channel using discrete units called bits. The data are represented as an electromagnetic signal such as an electrical voltage, radio wave, microwave, or infrared signals. Thus, the prototype will generate a amplitude shift keyed signal with a carrier frequency of about 35 kHz, and the keying signal is a digital signal of about 20 kHz. In order for a digital signal to be transmitted, it must be modulated in some way. Amplitude shift keying is the most basic way to modulate a message signal. As you can see here, it makes use of a carrier signal which is many times larger than the bit rate of the digital signal. The amplitude of the carrier signal is proportionally varied based on the bit value of the digital signal. A binary 1 sends the full amplitude of the carrier, and a binary 0 is a lower amplitude or no carrier altogether. In ASK, it requires two input signal. First input is the binary sequence, and the second input is the carrier signal. Here, the most important point that we need to always consider is the second input, which is the carrier signal, which has more amplitude or voltage range than the input binary sequence signal. So, within the carrier amplitude range, we are going to modulate the binary input signal amplitude. If the carrier signal amplitude is less than the input binary signal voltage, such combination will result to an overmodulation or undermodulation effect. So to achieve perfect modulation, carrier signal should have more amplitude range than input binary signal. The schematic and the assimilation of the project is done through multi-SIM application. However, due to the enhanced community quarantine caused by the COVID-19, the PCB of the project was not done. As mentioned earlier, to produce an ASK signal, it requires two input signals. The first input is the binary sequence signal, and the second input is the carrier signal. As you can see from the simulation, we used two operational amplifiers, which is LM741. This is used to produce a carrier signal which has a more amplitude or voltage range than the input binary signal. This subsequently produces a carrier frequency of about 39 kHz to 39.3 kHz. The carrier frequency can be ultimately varied using the potentiometers that is present in the oscillator circuit. The amplitude shift keying modulation circuit is designed using the 555 IC timer as an unstable mode. Here, the carrier signal can be varied by using the R1, R2, and the capacitor. When the pulse is logic 1, the output frequency is around 1.09 kHz. When the pulse is logic 0, the frequency is 0 kHz. This means that at 0 kHz, the switch is open. With that said, the input binary signal is applied in the pin 4 of the 555 timer, and the output is generated at the pin 3 of the 555 timer, thus generating the ASK modulated wave. Lastly, the modulator is generated by using BC547BP transistor. The carrier signal is applied through the emitter of the transistor, and the pulse signal is applied through the base. So, the transistor amplifies the input from the carrier signal through the collector-emitter circuit. The output ASK signal produced displays a constant frequency and phase with varying amplitude, corresponding to the pulse signal generated. This concludes the simulation of the ASK project. The next video that you'll be seeing is the breadboard video results that was done before the ECQ was implemented. Once again, I am Earl Nestor Velasquez of B12. Thank you for listening.